That extremely fictional scenario may have been the kind of thing playing out in the heads of Soviet military leadership by the end of the 1970s. The US was nearing the launch of the space shuttle, and in totalitarian dictator fashion, the Soviets were becoming paranoid. They were convinced the economics of the shuttle simply did not stack up, and it must therefore have been intended primarily for deploying military satellites. Some went so far as to suggest it could be used as an orbital nuclear bomber, launched from Vandenberg to strike major Soviet cities with little warning. Now, to be completely fair, the shuttle was in part an asset for the US Air Force, and in retrospect, the economics did indeed not stack up. It was used to deploy secret payloads. Soviet fears were amplified when Reagan took increasing interest in the Strategic Defense Initiative. This absurdly ambitious proposal would see a cacophony of US assets deployed to low Earth orbit, capable of detecting and destroying Soviet ICBMs. If successful, it'd allow the US to conduct a first strike unopposed. The Soviets needed to demonstrate a counter to the US countermeasure. They needed the ability to destroy any future Strategic Defense Initiative satellites. And it'd also be nice to have their own orbital bomber. They decided they needed a spaceplane too. Before we get started, a couple of quick points. Buran Energia is a wildly complex topic. I simply cannot cover the full history, so this video will focus on some of the technical details. I've used a number of Soviet sources. This opens up the possibility of translation errors and, well, Soviet shenanigans. I've tried my best not to take any important statements from a single source, but I'll make it clear if that's the case. I'd like to make a special mention to Buran.ru, which is the definitive source for information related to Buran, Energia, and related projects. In addition, images were sourced from the Buran archive. If I make any mistakes, I'll post corrections in the subtitles. I'm also going to struggle with pronunciation. I'll just try my best. With something like Buran, it is important to distinguish between what actually existed and what was planned to exist. I'll make it clear when I'm discussing something that wasn't actually flown. There's also an entire chapter towards the end of the video on proposed improvements to the system. Buran is a goldmine for myths, some easily demonstrated as false, some more difficult to disprove, and some that are actually true. Some statements I make in this video may not match up with what you've read online forums or elsewhere on YouTube. All my sources are included in the description. Many of these myths stem from us desperately trying to compare Buran with the space shuttle, and that's unavoidable sometimes. I'll be making a few comparisons for the sake of context. However, when asking which was better, the answer is the space shuttle, because it flew 135 times. Buran flew once. Of course, if we ask which theoretically could be better if both of them had flown operationally, now that's a more difficult question. You'll need to make your own mind up on that one. To be honest, I just think Buran and Energia are utterly fascinating, and that's what I really want to communicate here. Finally, regulars of the channel will be familiar with Artem Tatarchenko's amazing 3D animations. Artem mentioned a few months ago that Buran is a topic that he has been fascinated with for years. It's something I'd wanted to make a video on but didn't know where to start. Not only has Artem provided the amazing animations for this video, but he also helped me with the translation and sourcing reference material. Footage of the OK-GLI test aircraft filmed at the Technik Museum in Speyer was captured by Artem. Unfortunately, I couldn't make it over there myself before the video, but I will visit sometime in the future. In 1974, Valentin Glushko was appointed as the program manager of the Soviet space program. He found himself in almost the opposite position of his past rival, Korolev. While Korolev had designed a huge rocket, the N-1, for interplanetary flybys, Soviet leaders pressed him to rush to adapt it for a potential crewed moon landing. The results were predictable. Glushko was in the early stages of designing a super heavy launch system to construct a moon base, But following the US announcement of the space shuttle, Soviet leadership were far more interested in having their own reusable spaceplane. Glushko managed to put forward a design capable of achieving both of these goals. The Soviets had already cultivated an affinity for spaceplanes. The Spiral project, established in the 1960s, had culminated in several orbital flights of the Bohr 4 spacecraft. These flights were used to verify aerodynamics and heat shield designs for the Buran orbiter. Of course, the Buran airframe itself was a copy of the space shuttle. There are plenty of stories of espionage, but honestly, I think these are overplayed. Most of the shuttle design was public domain. Though I'm sure there was some tomfoolery, most of the information was readily available to the Soviets. For atmospheric test flights, the OKGLI test article was created by fitting a Buran airframe with 4 AL-31 jet engines, best known for their use on the Su-27 fighter. This was capable of taking off and flying under its own power. Quite a contrast to the glide tests performed via the carrier aircraft for the US space shuttle. I'll link some videos that discuss the test's history here, because I just don't have time to go into detail. Regardless, the most interesting aspect of Buran wasn't the orbiter. It was the launch system, Energia. In fact, the majority of this video is going to be about Energia. It was fascinating in its flexibility. Take the orbiter configuration. Buran was side-mounted onto the external fuel tank with 4 side boosters. This was, of course, similar to the space shuttle. The external tank contained hydrogen and liquid oxygen propellant, again, just like the shuttle. The side boosters, however, were liquid-fueled with kerosene and oxygen, a contrast to the solid boosters seen on the shuttle. The crucial difference here was the placement of the main engines. The RD-0120 main engines were mounted on the tank and not the orbiter. A much touted advantage was that the orbiter didn't have to carry the dead weight of the engines once in orbit. I will admit, I think this advantage is overplayed. Buran had a stated, not demonstrated, payload to low Earth orbit of 30 tons, against the 28 tons of the shuttle. The Energia main engines were essentially simplified clones of the shuttle RS-25 engines. Since the external tank could be ditched on every flight, these 4 engines were non-reusable. Though the shuttle main engines had a high overhaul cost, I think the reusability was a price worth paying for a less than 10% reduction in payload capacity. But the placement of those main engines carried a far more significant advantage. The Energia launcher was completely independent of Buran. It could, and did, launch other payloads. Theoretically, up to about 100 tons to low Earth orbit. This was a major weakness with the shuttle. Sure, it could launch about 100 tons to low Earth orbit too, but 70 of those were the orbiter itself. The shuttle system depended on the orbiter. And that was really just the beginning of Energia's flexibility. Take a single side booster, add a second stage, and now we have a Zenit rocket. In some cases, an RD-58, also present on the Buran orbiter, was added to form a third stage, capable of launching 13.7 tons to low Earth orbit. The Zenit was a completely independent medium-lift launcher that was only recently retired from service. We can also shrink down the core stage to just use a single RD-0120 and add 2 side boosters, and we get the Energia M, a more capable medium-lift launcher, theoretically able to deliver up to 35 tons to low Earth orbit. Energia M was actually the last launch system designed by the Soviets. A full-scale mock-up was constructed and even stacked up on the launch pad. In fact, it still survives today. So, those are the variations of Energia that were actually built. But there were other possibilities. Up to 8 boosters could be theoretically added to the core stage. And then we could even stack an Energia M core stage on top of that, and you'd get a Vulcan. This was Glushko's moon rocket. It would have been the largest rocket ever built, but it never was built, so we need not discuss it any further here. At the cost of throwing away 4 extremely expensive main engines every launch, Energia wasn't just a launch system. It was a potential family of launch systems, all sharing common hardware. We'll come back to the Zenits later, as they had a long launch history, but as for Energia itself, it flew twice, Following a number of shuttle launches carrying classified payloads, Soviet leadership had grown increasingly paranoid about its military capabilities. They were keen to publicly state that the Soviet space program was solely for the betterment of mankind and never for the militarization of space. In May 1987, they demonstrated this by launching a 95-ton laser into orbit. Polyus was, and still is, the heaviest satellite ever launched in one go. It was a demonstrator for the Skiff-class orbital weapon platform. This was designed as a counter to the US Strategic Defense Initiative satellites, theoretically able to destroy them and nullify the US countermeasure. A full disclosure, Polyus wasn't actually equipped with the laser, it just had the tracking system. It was just a demonstrator for future Skiff satellites. In the scenario I presented at the start of this video, I also armed a Skiff with a point defense cannon. There are references to defensive cannons being added to Soviet satellites, so I just went with it. Because, as fans of The Expanse know, PDCs are way cooler than lasers. Let's just ignore the fact that neither could stop a kill vehicle on an orbital intercept. Anyway, Polyus was launched on the back of an Energia from Site 110 in Baikonur. This is the same complex from which the doomed N-1 moon rocket was launched, resulting in one of the largest man-made non-nuclear explosions in history. And Energia very nearly repeated that feat. It pitched over away from the launch tower for the first couple of seconds after launch due to a software restriction on nozzle gimbling. After that, the guidance software was able to take over, recover, and ultimately deliver Polyus to its intended speed and height. Unfortunately for the Soviets, Polyus's guidance system malfunctioned. The orbital injection burn failed and it fell back to Earth. But this was unrelated to Energia, which, despite the precarious launch, did its job exactly as designed. Energia's second launch was the really spectacular one, because that was the Buran flight. In my video about the space shuttle, I stated that to launch a vehicle for the first time, we either need to do something brave or spectacular. The first launch of Buran was spectacular, because it was carried out without a crew on board. In fact, there wasn't even a life support system installed. There were no payload bay door opening mechanisms, no fuel cells, no radiators. It was a bare minimum reach orbit and get back mission. Surprisingly, it did carry a cargo though. A 7-ton module referred to as the 37KB was stowed in the cargo bay. There's little information available on this module, but it served two purposes. One was carrying additional measurement and power equipment to evaluate the test flight itself. The second was to act as an additional living space for future crew, much like the pressurized modules on some of the shuttle flights. And this first flight was to evaluate that capability. The impression I've been given is that the team by this point were just desperate to launch the thing before their country collapsed. Gorbachev, the guy from the Pizza Hut advert, had previously visited Baikonur ahead of the first Energia launch and cast doubt on the future of the entire program. Buran's original military purpose was obsolete. The country was imploding. The Cold War was about to end, and both sides wanted to ensure it ended without going hot. The first launch attempt was on the 23rd of October 1988. The orbiter designated OK-101 was rolled out to the launch pad on the back of an Energia stack. But the launch was aborted seconds before liftoff due to a computer fault. The next attempt was on the 15th of November 1988. At 8 AM local time, the 4 RD-170 engines of the side boosters and the 4 RD-0120 engines of the core stage came to life, and Energia carried Buran clear of the launch pad and almost immediately into a low cloud ceiling. The Soviets could certainly build a great launch system, but they never seemed to master half-decent video cameras, though this may have been deliberate, of course. So the launch footage isn't great. At T plus 144 seconds, the side booster engines were shut off in pairs, and the boosters jettisoned. At T plus 476 seconds, the core stage engine shut down and the core was jettisoned, placing the orbiter on a ballistic trajectory. Near the apogee, the onboard RD-58 engines were ignited to bring the vehicle up to orbital velocity. They were restarted again halfway around the world to put Buran into a 255-kilometre orbit. Buran proceeded to orbit the Earth twice, sending back telemetry data and video from its onboard cameras. As it passed over the South Pacific for the second time, it started up the onboard engines for the third and final time to perform the deorbit burn. The landing is the phase of the flight that's become somewhat legendary in the spaceflight community, and for good reason. Let's take a look at the situation as Buran was entering its pre-landing manoeuvre. The target runway at Baikonur is roughly east-west oriented. That morning, there was an approximately 15 metre per second wind with a 205-degree heading. At the point of deorbit, this information had been passed on to the spacecraft, which correctly selected a landing in the westerly direction to ensure it was landing into the wind. At an altitude of 20 kilometres, the re-entry phase was complete, and the RCS thrusters had already been disabled. Buran was operating like a conventional glider, with control surfaces providing attitude control. The flight control program had access to the meteorological and atmospheric data from a combination of onboard sensors and ground stations, which provided it via radio uplink. As we'll discuss later, the program also had some adaptability and was able to discern the orbiter's handling characteristics, which would always carry some uncertainty due to varying load balance, aerodynamic performance, and other factors. The aim was to fly by the runway in the direction of the wind with excess energy. This would essentially guarantee the craft could reach the runway. Then this energy would be bled off by performing a course correction turn. Depending on the speed and altitude at which this turn was entered, it could be widened or narrowed to ensure the excess energy was exactly bled off just as the spacecraft entered the final approach to land, placing it exactly on the correct glide slope at 4 kilometres of altitude. Buran had the choice of two virtual cylinders to make the turn in, referred to as course correction cylinders. They sat within a larger area referred to as the energy dispersion cylinder. Buran's computer had full agency over whether to pick the northern or the southern cylinder. Prior to entering the pre-landing manoeuvre, and at an altitude of around 30 kilometres, it had already picked the southerly route. So, a gentle right-hand bank to follow the southern cylinder was what everyone on the ground was expecting. But remember that 15 metre per second wind? That had increased the glide time if the orbiter turned into it too soon. Buran was coming in with too much energy, but no one on the ground really knew that. So, try to imagine their surprise, and the surprise of the MiG-25 chase pilot who was about to take off, when Buran went into a 45-degree left bank. Multiple accounts from the control room talk of senior officials preparing to fire the self-destruct explosive charges on their multi-billion-ruble spacecraft, which appeared to have gone rogue. It then entered the northern cylinder and performed a gentle 270-degree right-hand turn to put itself on final approach for the runway.
The unmanned shuttle went into space about 3.5 hours ago. It completed 2 full orbits before returning to Earth. Soviet TV said all sims worked properly during the flight.
And the landing was as perfect as the liftoff. The shuttle's white fuselage was now almost gray from heat generated during re-entry.
The next flight is expected in the middle of next year, this time with cosmonauts at the controls. That will be the real test. If it works, they'll begin launching the building blocks of a spaceship that will one day take them to Mars.
This moment was the culmination of a decade of work by hundreds of thousands of participants in a country that was falling apart. In the coming months, a series of revolutions would dismantle the Eastern Bloc, with the Soviet Union as a whole collapsing shortly afterwards. Given these circumstances, it's a miracle Buran flew at all, but it did. We will never know whether Buran could compete with or even improve upon Western launch systems, but thanks to this one flight, we'll always know one thing: Buran worked. Now, there are a couple of myths I'd like to briefly discuss. First is the wind speed. I've heard some skepticism about the 15 metres per second crosswind. I think it comes from people who are used to seeing airliners with their high aspect ratios performing crosswind landings. Something like Buran is basically the opposite, so you're not going to see the same effects visually. It is an impressively high wind speed for a first test flight, and the first uncrewed landing of a spaceplane. I've scoured the videos looking for a windsock, but I can't find one anywhere. But look at these folks posing with Buran just after the landing. Yeah, it was windy. Even if the landing had been performed on a calm day, it'd still be amazing. But based on the footage, I think the wind speed claims are true. I also found what are claimed to be the original forecasts, and again, they do match up with the claim. Secondly, the unusual and unexpected manoeuvre. It's often said something along the lines of there was a 3% chance of Buran performing this manoeuvre. I've even seen claims it diverted to avoid a storm or landed at a secondary airfield. I think this is mistranslation combined with internet myths, as the statement doesn't really make sense by itself. Buran performed the manoeuvre, so there was a 100% chance of it doing so. I believe what is meant here is that once the orbiter had reached the point in its flight, the atmospheric and flight conditions to trigger a switch to the other correction cylinder were expected in only 3% of flights. These conditions were triggered on the flight, so the computer correctly amended the course. The Soviet government lied about everything they had the chance to, but there is no need to lie or exaggerate. Buran's first flight was a stunning achievement. Presented with one of the largest rockets ever built, I'm the kind of person to take a look and ask, yeah, but how was everything transported to the launch pad? If you've made it this far, you're probably that kind of person too. So here we go, the logistics chapter. Let's start at the launch pad and work our way backwards. The Buran Energia stack was transported to the pad via a mobile transport unit. You may be familiar with the crawler transporter unit NASA used for the Saturn V, the shuttle, and the SLS. Buran's transporter unit was completely different. First of all, the Buran Energia stack was transported horizontally and raised to the vertical position by 2 pairs of hydraulic jacks on the unit. I imagine this had placed extra strain on the vehicle during stack-up and transition to the vertical, but it probably made the stack-up process itself simpler. Horizontal transport was necessary at Baikonur due to the frequent high wind speed. The second major difference from NASA's transporter is the method of propulsion. It was towed by diesel locomotives. Much of the infrastructure at Baikonur is rail-based, which feels very Soviet. Of course, as someone from a country famed for its terrible railways, I'm impressed and intrigued by this rail-based approach. I also want to mention the escape slides from the launch tower, which could be used by cosmonauts and ground crew to evacuate in case of emergency. To get up the tower, crew would ride these little trolleys up an adjacent tube. I think they're great. They look like something from a campy 1960s James Bond film. Prior to rollout, the stack-up was integrated in the MZK building using an overhead gantry crane and loaded onto the transporter. Individual components, including the orbiter itself, were transported to this building using an MAZ-537 tractor and special trailers. But how were these huge components delivered to Baikonur? This is a problem the Soviets struggled with for years. One proposal devised a special rail link to the cosmodrome capable of carrying the huge tanks, boosters, and orbiter. This was deemed too expensive and infeasible. Another proposal saw 2 Mi-26 helicopters share an underslung load in flight trials. This would have potentially been extended to 4 helicopters for large components such as the fuel tank. This proposal went no further because it was clearly ridiculous. A heavy fixed-wing airlifter was required. The long-term plan was to modify one of the newly designed Antonov AN-124s to perform the job, but this was going to take years to achieve. An interim solution was needed. Realistically, there were 3 aircraft available to the Soviets that could potentially be modified to carry the Energia components. The Milot 3M, NATO reporting name Bison B, the IL-76, NATO reporting name Candid, or the AN-22, NATO... Actually, let's not worry about NATO names. Here they are listed by their max nominal internal payload. Here is the maximum mass of an Energia component that would have had to be lifted to Baikonur, mounted externally on the aircraft. Which one would you pick? Which one do you think the Soviets picked? And the answer is, of course, the Molot 3M. Okay, I'm being a little deceptive. There would have been many factors other than just nominal payload when deciding which aircraft to modify for this task. But carrying almost double the design payload and carrying it externally was a big ask. 2 Molot bombers from the 1960s were modified to carry the tanks, boosters, and orbiter itself. I became a little obsessed with these aircraft while researching this video. How is it that the Soviets were able to so consistently build aircraft that were simultaneously ugly and beautiful?
Apart from its large twin vertical tails and the carrying attachment on the fuselage, the Atlant is basically the same as its ancestor, which was first seen in public at the Soviet Aviation Day flypast in 1954.
Okay, I'll have to stop you there, well-spoken British man. Though this looks incredibly janky, extensive and meticulous work went into these modifications. These aircraft were a far cry from just strapping a big tank to the top of an early Cold War bomber. The original designer of the Molot and legendary aircraft designer Vladimir Misisheva was heavily involved in the project, which is probably the reason it was even considered in the first place. Following wind tunnel tests, a new extended empennage was fitted with twin vertical stabilizers to the aging aircraft. To bear the weight of this new fuselage extension and the proposed cargo, extensive strengthening was added to the airframes, along with new landing gear. An augmented stability system, irreversible hydraulic controls, and new uprated engines were fitted to carry the Buran and Energia components with at least some semblance of safety. Misisheva died early in the project, and the aircraft were renamed the VMT Atlant. VM for Vladimir Misisheva, T for transport, and Atlant as a reference to the Greek god Atlas, who will be appearing again in this video. Though the Atlants could barely make it off the runway, requiring a 3.5 kilometre run to take off, and drogue parachutes to stop on landing, they went on to conduct 150 flights to ferry parts for Buran and Energia. One of them came close to destroying an orbiter and itself when 2 engines were lost on final approach to the runway, but the aircrew were able to avert disaster and put the aircraft on the tarmac safely. In an earlier test flight, an Atlant carrying an orbiter mock-up skidded off the runway and got stuck in mud long enough for a US spy satellite to capture a photo. I'm gonna be honest, that's pretty hilarious. Nevertheless, the aircraft performed admirably and have gone down in history as one of the most unusual configurations ever flown. Just weeks after Buran flew for the first and last time, the Atlant's replacement was ready. I want to say the Atlant was the little plane that could, but it was still a big aircraft. It's just that its replacement was an absolute monster. This is what we're all here in the logistics chapter for. The Antonov AN-225. The events of September the 11th, 2001 shook the aviation world. By events, I'm of course referring to the 1,000-kilometre flight the AN-225 took on the morning of September 11th, 2001, carrying 5 main battle tanks totalling 253.8 tons. That is the heaviest load ever carried by an aircraft. Now, that figure's often quoted, but I think we need to put it into context. The Boeing 747 is the aircraft capable of carrying the heaviest payload that most viewers will be familiar with. How much do you think a Boeing 747 can carry? 90% of the AN-225, maybe 80%? The answer is 132 tons, just over 50% of that of the AN-225. The only aircraft capable of carrying more than a 747 is the AN-124, and that can manage just 150 tons. still absolutely nowhere near the AN-225. It's rare for anything to be the largest by such a margin. I think it's just difficult to stress how huge this thing was. Until recently, I always thought the AN-225 was just that. Huge. Extremely impressive, but I assumed it was a signature piece of Soviet build it large but low tech. In keeping with the rest of the Buran program, that turns out not to be true. For starters, it was equipped with a favourite technology of this channel, fly-by-wire. And this was only 1 year after the first commercial airliner with digital fly-by-wire first flew. It was also fitted with a unique and highly mechanically complex landing gear assembly. It had internal bedrooms for flight and ground crew, and it had 4 internal cranes for cargo loading. It was capable of travelling over 4,000 kilometres whilst fully laden without refuelling. Truly a triumph of late Soviet engineering. It deserves more discussion from me, and I will almost certainly be revisiting it in a future video. Let's focus on the Buran orbiter itself for this chapter. I'd like to come at this from mainly a crew safety perspective. This chapter will be the closest I get to a direct comparison between the Space Shuttle and Buran. Of course, I'm not going to tell you whether one was theoretically safer than the other, because, as always, it's about trade-offs. Let's begin with what may be the most pervasive myth about Buran: ejector seats. In much of the contemporary literature, we see a similar phrase echoed again and again. Buran was planned to have ejector seats for all of the crew. Indeed it was, because all the scheduled flights for Buran were test flights with a crew of 2. So whether this is deceitful wording from the Soviets or a half-truth that was built up over time, I'm not sure. Of course, Buran never flew with ejector seats, because it never flew with a crew. But the orbiter that flew was built to accommodate 2 ejector seats. The ejection hatches are clearly visible. A considerable effort was put into designing and testing these seats, along with the flight suits, to ensure they'd permit ejection of the 2 crew members up to a speed of Mach 3, or about the point of booster separation. You know what else had 2 ejector seats rated to about Mach 3? The Space Shuttle. Despite what you may have heard elsewhere, as built, Buran had about the same crew eject capability as the shuttle. We'll come back to theoretical additional ejector seats in a second. In the years since the Soviet Union collapsed, various individuals involved with Buran have made unfounded statements about ejector seats for a full crew of 8, or even 10. And they're just that, unfounded. I don't like to use the word impossible, but ejecting 4 crew from the flight deck and 4 from the mid-deck, not going to happen. And I've found no evidence it was ever planned to happen. But that didn't mean Buran didn't have the potential to be safer for crew than the shuttle. I believe there were more pathways open to Buran for crew safety than were available to NASA. Whether these pathways would have been taken is something we'll never get to find out. Let's start at the highest level and work our way down to more detail. During the 1980s, NASA had a total of 1 crewed launch system available, the Space Shuttle. Roscosmos had 2, Buran and Soyuz. They also planned to build a crewed capsule for Zenit, but that never actually happened. After the Challenger disaster, I think there's a reasonable chance the Soviets, or the Russians, would have never flown a Buran with more crew than available ejector seats. Why go through all that risk when it was possible to launch 2 members in a Buran and the rest in a Soyuz and dock the 2 later? Of course, we can argue that 2 or even 3 launches and docking procedures are more risky than 1, but with 2 decent crew escape systems, bit more ambiguous. This represents one potential path to improve crew survivability. The availability of an additional launch system also opens up paths for orbital rescue that were not available to NASA. As I discussed at length in the last video, the Columbia disaster was more a product of flawed safety culture at NASA. But had they taken the threat seriously, Their options to rescue the crew were shaky at best. Assuming the Soviets were able to recognize and respond to a similar situation, and that is a huge assumption from the same people that bought you Chernobyl, a Buran rescue using either a Soyuz or a second uncrewed Buran would be far more palatable. Let's zoom in and look at some system specifics. I said Buran had basically the same crew eject capability as the shuttle. Now, that's not entirely true. There was something present, but its usefulness is highly debatable. In the case of a catastrophic failure on Energia, the orbiter could perform an emergency detach by firing 4 solid rocket motors housed on the underside of the nose. Depending on the altitude, the autopilot would then glide to a safe landing, or the crew would eject. Even the engineers working on Buran expressed doubts this would have any chance of saving the crew. Suddenly forcing the orbiter into a supersonic airstream with only milliseconds for the control surfaces to respond seems optimistic at best. And we have a precedent. Contrary to popular belief, Challenger wasn't destroyed by an explosion. It was pushed free of the SRBs and external tank into the airstream and disintegrated. And it was travelling at just under Mach 2 at the time. The emergency disconnect system can be thought of as an absolute last resort. The Buran that flew to space only had the capability for 2 ejector seats, but on a good day, a really good day, you could convince me it was possible to build a Buran with 4 ejector seats. And that seems to at least have been a preliminary intention. For reasons I can't figure out, 2 additional seats wouldn't be in the flight deck. Perhaps adding an additional blowout hatch in the roof wasn't possible for structural reasons. But the proposal was to seat 2 crew members right at the front of the mid-deck. A blowout hatch should be installed forward of the flight deck windows, allowing the additional crew to eject. I am really sceptical this would be possible, not least because there was a structural cord in the way that would somehow have to be explosively removed too. In fact, Orbiter 201, which began construction and was touted to be designed for a crew of 4, didn't have visible ejection hatches. But the reason this could maybe be possible in the first place is the smaller volume taken up by the forward RCS system. The forward propellant tanks in the shuttle made that system larger overall, so forward upward ejection from the mid-deck could be more difficult there, even if the avionics bay were moved. I should say Buran was designed to have optional additional DOM propellant tanks in this area for long-duration missions. It's unclear whether these would impede hypothetical ejector seats. Again, highly hypothetical, but another potential path to improved safety. There's one more major factor concerning crew ejection, the side boosters. They were liquid-fueled rather than the solid boosters on the shuttle. Now, in my last video, I stated that history shows for systems without a crew escape system, solid rocket boosters are overall more safe. That's because they essentially cannot fail due to a loss of thrust, and they're less likely to fail catastrophically than a complex liquid-fueled assembly. Yes, I know one failed prominently in the case of Challenger. If you want to hear me talk about that for 40 minutes, here's my last video. If we consider Buran carrying a full crew without ejector seats, the presence of not 2 but 4 liquid boosters almost certainly increased the risk of loss of crew due to a loss of thrust or a catastrophic failure. But considering a crew of 2, or possibly 4 if ejector seats were present throughout, unlike solids, liquid-fueled engines could be shut down. That potentially makes ejection safer, as the crew wouldn't have to clear a superheated plume of gas and SRB fuel. In short, a higher chance the crew would need to eject, but a higher chance of survivability if they did. We'll explore abort modes due to booster failure soon, but now I think it's time to talk about those liquid booster engines. Let's do the engine chapter. What was the most powerful liquid-fueled rocket engine ever flown? If you clicked on this more than hour-long video, you probably already know the answer is not the F1 from the Saturn V. It was the RD-170, the engine for Buran's boosters. The F1 is often regarded as relatively crude but very large. That isn't really true. It was a nightmare to design, and much of its complexity lie in mitigations for combustion instability. This is an entire family of issues, but in short, I don't think you even need to be an engineer to see something like this and see a great big resonance chamber. Combustion instability can drive alternating high and low pressure zones within the engine, causing it to tear itself apart. When I first started reading on the matter, I imagined these oscillations being around the order of 1 bar and a few hertz. Then I watched this lecture by Dr. William Sirignano, where he spoke of 200 bar oscillations at 2 kilohertz, which is, how the hell do you deal with that? The Soviets tended to build engines with multiple combustion chambers. These would weigh more than a single chamber equivalent, but not require some of the complex geometry and injector design seen in US engines. Multiple smaller chambers are less susceptible to combustion instability, so engines like the RD-170 would share a common turbopump and plumbing, but feed the propellant into multiple chambers, 4 in the case of the RD-170. I've spoke about engine architecture at length in the past, so here's a very quick recap. A rocket engine burns fuel and oxidizer in a combustion chamber to generate fast-moving exhaust, which provides thrust. To get our propellants into that chamber, we need them to be above the chamber pressure, which, as you can probably imagine, is generally quite high. For the RD-170, it was over 200 bar. To drive those pumps, most engines burn some fuel and oxidizer in a pre-burner and use the exhaust to spin up a turbine which drives the pumps. This assembly is called a turbopump. The simplest approach for large engines is to run the pre-burner fuel rich. This keeps the combustion temperature lower and therefore reduces the demands on the turbine. The fuel-rich turbine exhaust is dumped overboard. In my last video, I showed how NASA were able to create a closed-cycle engine by feeding that fuel-rich exhaust back into the main chamber in the RS-25 engine. But that was only possible because the RS-25 burned hydrogen. It was also fiendishly mechanically complex. The RD-170 was fueled by kerosene and liquid oxygen. There's no known way to build a closed-cycle engine that uses those fuels in a fuel-rich pre-burner, as the carbon-rich exhaust would just clog up the injectors. But there was, the forbidden method. Run the pre-burner oxidizer rich. Let's take a look at the RD-170's architecture to understand more. Starting with the pre-burner and turbine. In fact, there were 2 pre-burners. 2 were required to get the 1.5 tons of liquid oxygen per second through the system. Okay, let's just pause there a second. 1.5 tons of liquid oxygen per second. There are going to be a lot of numbers in this section that are completely outside of my normal operating context. There's a reason I chose to do an entire chapter on this engine, because it's unlike anything else I've ever read up on. Anyway, those 1.5 tons per second of oxygen were used to burn a comparatively small amount of fuel and drive the turbine. And that again takes us straight out of my operating range. This is why I refer to the oxidizer-rich closed cycle as forbidden. A very high pressure, 500 bar, and high-speed turbine operating in almost pure and high-temperature oxygen, up to about 600 degrees centigrade. I don't know how to design an alloy that can operate under those conditions. And neither did the Americans. They believed it impossible to run a turbine oxidizer-rich with practical technology of the time. It was only after the collapse of the Soviet Union that the West learned the Soviets had been building oxidizer-rich closed-cycle engines since 1960. Honestly, this may have been the field where the Soviets exceeded the West by the greatest margin. That turbine drove both the high-pressure fuel and oxidizer pumps on a single shaft. We've already learned the oxidizer pump had to move about 1.5 tons of oxygen per second, boosting it to 600 bar. The common shaft also drove the fuel pump, which moved 650 kilograms per second of kerosene, boosting it to 500 bar. Some of this fuel was tapped off and sent through a second stage, boosting it to 800 bar. We'll take a look at where these outputs went in a second, but let's just note those unusually high pressures and flow rates. The total power of this turbopump assembly was 170 megawatts. Again, just totally outside of my operating context. The Soviets seemed fond of expressing this power like this. Remove the turbine and just leave the pumps. Take 3 nuclear icebreakers, 3 of this one specifically, wrap tow lines around the turbine shaft and connect them to each icebreaker. Then have them steam ahead at full power. That would drive the pumps with the same power as the turbine we just removed. All just to get the propellants in the combustion chamber. And remember, that turbine's spinning at 14,000 RPM in almost pure hot oxygen. The output of the oxidizer pump was split between the 2 pre-burners, with all of the high-pressure oxidizer sent to them. This was burned with a small amount of fuel, and the hot oxygen-rich gas was sent to the hot gas manifold. This delivered the hot gas to all 4 combustion chambers. But to simplify things, let's just show one of them here. A small portion of the hot gas was tapped off and passed through a heat exchanger. This heated helium from onboard supply bottles to pressurize the propellant tanks as they were depleted. After passing through the heat exchanger, the hot gas drove a turbine connected to the low-pressure oxidizer pump, which pumped the fluid directly from the oxidizer tank. All of this oxygen was routed into the oxidizer pump, completing the oxidizer pathway in our diagram. The outlet of the first stage fuel pump was fed into the walls of the combustion chamber and nozzle for regenerative cooling. I think an animation speaks 1,000 words here. This is how the fuel was directed around the nozzle and chamber through hundreds of machine channels. The heated fuel was collected in a manifold and sent to the mixing head. This consisted of hundreds of injectors which mixed the fuel with the oncoming hot oxygen-rich gas, creating combustion and generating thrust. The arrangement of the injectors in the head was complex. Injectors with different flow rates were situated at different points. This arrangement had been painstakingly devised through extensive experimentation to reduce the effects of combustion instability. Turns out that despite the 4-chamber layout, the RD-170 still needed this complex injector layout. The regenerative cooling was still insufficient to keep the nozzle intact, so up to 2% of the fuel injected into the chamber was sprayed directly down the walls and nozzle walls by special injectors to provide film cooling. The Rocketdyne F1 engine cleverly used the relatively cool turbine exhaust to do this, but the oxygen-rich turbine exhaust of the RD-170 had destroyed the nozzle at these high temperatures. The 2% wasted fuel was more than offset by the additional efficiency of the closed cycle. To complete the fuel circuit, let's return to the fuel pump. A small amount of high-pressure fuel was tapped off and used to drive the low-pressure fuel pump, which draws fuel directly from the tank. All of this low-pressure fuel is sent to the fuel pump inlet. An additional 20% of the fuel was tapped off and sent to the Stage 2 fuel pump. This boosted the fuel pressure to 800 bar where it was fed into the pre-burners, allowing combustion to take place and drive the turbine. With fuel and oxidizer flowing into both the pre-burners and combustion chambers, that completes the propellant pathways for the RD-170. There's one more feature I'd like to point out. If you watched my last video, you may mistake this small tank for a pogo suppression system. In fact, it contained a small amount of fuel, separated from the helium supply by a diaphragm. To start the engine, high-pressure helium was injected, forcing the starter fuel into the system. This had burst discs holding back triethyl aluminum starting fluid in these cartridges here. This fluid ignites on contact with air, so would start the turbines and ignite the propellants in the combustion chamber, starting up the engine. Again, I don't have time to go into the history, but the RD-170 was a nightmare to design. At least once an engine test in front of a gathered bunch of high-ranking officials and dignitaries exploded, which I find hilarious. The RD-170 project narrowly avoided cancellation multiple times, and the design was only finalised after over 200 development engines had been built and tested. For comparison, the F1 required about 100 development engines, and that was considered a nightmare that almost grounded the Saturn V at one point. The final result, though, was undeniably a masterpiece. 7.9 meganewtons of thrust in vacuum, and a specific impulse of 337 seconds. It was designed to be reused 10 times, and this capability was demonstrated with repeated test firings. This represents a level of performance that has not since been matched for a kerosene liquid oxygen engine. Throughout its entire history, the Soviet Union lagged behind the West in terms of computing technology. That makes Buran's guidance system all the more impressive. Though behind the West in terms of hardware, the country was beginning to gain a reputation for code development, particularly in the fields of statistical analysis and data processing. Based on the work and how it was implemented, I do wonder if Buran was a catalyst for this. Buran operated on a quadruplex system. That is 4 independent flight computers reading commands from 4 independent memory banks. A failure of a single computer was detectable by the others, and the outputs would be discarded from the faulty machine. Likewise, a double computer or memory failure would still allow for safe operation. However, this entire system was then replicated again, so there were actually 2 independent quadruplex control loops. So, if an unanticipated failure mode rendered all 4 computers out of action, the second loop could assume control. There was additional redundancy available in the data buses and sensor packages. We don't have time to go into full details, as this chapter is more concerned with software. It seems the process of software development for Buran was unusually open and progressive for the Soviets. As the scale of the challenge became apparent, it was realised potentially hundreds of developers would be necessary to write the code. And these developers would need to communicate with engineers, test pilots, and other decision makers. The decision was therefore made to create an entirely new programming language for Buran. There's very little information available on this language. It was called Prol-2, sometimes mistakenly confused with Prolog, which is an unrelated language. Unlike the lower-level assembly code typically used for flight control systems back in the 1980s, Prol-2 was a higher-level language and was therefore more accessible to both developers new to the team and also to less technical staff. After Buran, these principles were condensed into a visual programming language, Drakon, which saw some use in the Russian space program during that period. All of the material I could find regarding the development process was in Russian, but after translating, the language is pretty familiar to any modern-day software developer. There are repeated references to a subroutine hierarchy, with lower-level subroutines running repeatedly in the background to monitor spacecraft health and to constantly determine velocity, position, and perform any corrective actions. Higher-level subroutines would be called as and when necessary, with the code following a modular structure. Buran's software had 14 available modes, with the appropriate mode active for each relevant portion of the flight. Repeated testing from individual code units all the way to physical flight testing ensured individual modules could be quality assured and reused or adapted for use elsewhere in the software. Subroutines were prioritized by what appears to be an executive operating on a 32 millisecond cycle and able to select subroutines to run, to queue existing subroutines, and to reprioritize if necessary. This is a similar principle to that used on the Apollo guidance computer. As for flight testing, that was performed extensively on OKGLI. In interviews, pilots speak of teaching Buran to fly. It makes it sound like they were training up machine learning algorithms, but that won't have been the case. This was the 1980s after all. That is, unless you define machine learning as any kind of statistical model, which is what tech companies used to do a few years ago. They just say AI now, which is even worse. The software will have had built-in models, and these models needed known parameters to be usable. Take control surface movement as an example. This would have used what's called a PID algorithm. Applying a given deflection to a control surface had caused the spacecraft to move in a certain direction at a certain rate, and that would depend on many factors such as airspeed, air density, temperature, state vector, so on. Much of the time spent on test flights would have involved applying known inputs to the control surfaces and recording how the spacecraft responded. With enough input-output combinations, models would be built up and the vehicle's software would eventually be able to anticipate the relationship between inputs and outputs. That is what is meant by teaching Buran to fly. Understanding exactly how the guidance algorithms worked is difficult, not least because they've never been made public. But there is enough material on the matter available for me to form a rough picture. Let's just focus on the pre-landing stage of descent, since that is the one where the orbiter made the most blatant display of its autonomy. The objective of this phase was to get Buran from 20 km altitude to a target altitude of 4 km and in line with the runway. There were of course constraints on hitting this target. Buran had to stay within the energy dispersion cylinder. It had to make a turn in one of the heading adjustment cylinders. And I presume minimising the maximum distance from the runway was also a condition. So this is an optimisation problem. There are many potential approaches, but Buran used some kind of path-following algorithm in conjunction with some kind of gradient descent. On hitting an altitude of 20 kilometres, the computer determined a reference trajectory to get the orbiter to its target. From what I understand in the publications, the reference trajectory wasn't strictly a physical path. Rather, it was a list of altitudes and the corresponding total energy the orbiter should have at those altitudes in order to hit the target. Buran could calculate its total available energy at any point via onboard measurements and from data transmitted from the ground. As time proceeded, Buran would compare its current energy to that of the reference trajectory. It'd continuously take corrective action to maintain or lose energy, keeping the total energy as close to the reference trajectory as possible. Energy could be lost through manoeuvring or by increasing the angle of attack. And that is why Buran took the unexpected route to land. Though the guidance algorithm may not have been looking ahead to the northern course correction cylinder, a turn in that direction was permissible. And at the time, a turn would begin to take the energy down closer to that of the reference trajectory. Hence the term gradient descent. The algorithm didn't look far into the future, it just looked one time step ahead to decide which direction to take right now to get closer to the reference trajectory. And that trajectory would take Buran to its final goal. As time progressed, the algorithm minimised the difference between actual and desired energy, one step at a time. Finally, to address the inevitable comments on how, with some hardware modifications, the space shuttle could also theoretically fly and land itself. Maybe it could, but it never did. And on the subject of could and did, we've already mentioned components that were planned but never flown, such as ejector seats, RCS propellant extender tanks, and crew. There are a few others I'd like to briefly discuss. When naive comparisons are made between Buran and the shuttle, these components are often included in the discussion without consideration for the fact they were never actually flight-proven. So I've decided to pick 3 examples that were actually built and tested on the ground. They just weren't integrated into the only flight. The odd-looking protrusions on the boosters were there for a reason. They were to house extendable legs and solid rocket motors to aid with booster recovery. As these rather aesthetically pleasing illustrations show, the boosters were to be recovered by parachute for reuse. Had Buran flown operationally, booster reuse would be essential for the program to be economically viable. Throwing away 4 RD-170 engines per launch would never have worked. NASA were able to recover the solid rocket boosters on all but 2 shuttle launches. For this reason, I think it's perfectly reasonable to believe the Soviets would have been capable of achieving booster reuse given the time. A land recovery of such a large booster would be difficult, but they were designed for it from the start. Had Buran flown for a second time, it would have carried at least one remote manipulator, colloquially known as a robot arm. The equivalent on the shuttle, the Canadarm, was one of the more successful aspects of that program, proving essential for payload deployment, on-orbit construction, and astronaut transport. Buran was designed to carry 2 manipulators, and they could be operated remotely from the ground. I've included a mention of them because they were actually built and tested at a facility in St. Petersburg. Whether the remote operation capability was practical back in the 1980s is something we'll never know, but the majority of work carried out by the ISS's manipulator arms today is carried out remotely from the ground. A problem the Soviets faced was the location of the launch site in relation to potential abort locations. Launching east from Baikonur, an abort during ascent carried few potential airfields for an emergency landing. The shuttle, on the other hand, had a selection of abort locations across the Atlantic, situated in friendly countries. As for a failure earlier on the ascent, options for the shuttle weren't great. The return to launch site option was possible, but it'd be tricky to pull off in reality. Buran originally was designed to manage both of these abort cases by extending its glide range. This would be achieved by equipping the orbiter with 2 of the same AL-31 turbojets used on the OK-GLI test aircraft. They'd be housed in pods protected by thermal tiles. Upon entering the lower atmosphere, intakes on the front would open and the engines would be started. 2 engines would not be enough to achieve positive lift, but they could extend the glide long enough to reach a landing site. Had the turbojets been fitted, they would have mitigated some of the risks of an RTLS abort and would have represented a genuine safety improvement. However, they were not. Prior to the first flight, it was decided not to fit them and fill the resulting cavities with heat tiles. Buran was close to flying with these engines in place, though. There are even photos of the throttle lever present in the cockpit. A common thread with all these proposed additions is they all eat into the payload capacity of Buran. The turbojets would weigh 400 kilograms each and require fuel and additional control systems. I don't know how much booster recovery it'd take from the payload, but 4 sets of landing legs and motors would have a material impact. Even a single robot arm weighs about half a ton. The Cold War often devolved into world leaders getting their AN-22s out and having a measuring contest. And Buran versus shuttle payload to orbit is one such measuring contest. Advocates for Buran over the shuttle are sometimes overly keen to point out its marginally higher payload capacity. That capacity was never flight proven, and it's unclear whether it refers to the theoretical capacity of a stripped down orbiter that actually flew, or some other configuration. One of the modifications I have discussed would give Buran a capability that the shuttle never had. The other 2 would bring it to parity with the shuttle, at the expense of some payload. Though a thoroughly impressive system, we'll never know what the payload capacity of Buran truly was. One last completely unrealised development I'll have to mention, or else people will be mad at me, is something that was never built. Some of the findings from Buran were developed into a smaller, more economical spaceplane concept called MAX. I've come to some pretty interesting conclusions about it based on my research for this video. I will discuss it further in the future. Buran and Energia were sadly never able to live up to their potential. But the story didn't end with the final flight. In fact, Buran and Energia had an impressive legacy, and it's a legacy many are barely aware of. In this chapter, I hope to pick you all back up. We'll talk about the lasting impact of the project, and how it continues to have impact both in the world of spaceflight and even in other sectors. Hopefully you'll come away feeling happy. Then I'm going to break your heart. Zenit went on to become a reasonably successful launch system. 84 launches were carried out in total between 1985 and 2017, and 75 of those were considered operational launches. Of those, 8 were failures, so not the greatest success rate, but not unusually high for a pre-2000 launch system, to be fair. Of those, 3 were due to the RD-170, which powered the first stage, failing. If we include the 8 RD-170s that launched on Energia, that'd give a first-pass estimate of a failure rate for the engine of about 3.5%. But as we'll see in a second, I suspect they'd have been much more reliable had they been used on Energia. In 1995, a consortium between companies from Norway, the US, Ukraine and Russia formed Sea Launch. They converted a semi-submersible drilling rig into a mobile launch platform, specifically to launch Zenit rockets. Over their lifetime, they launched a total of 36 test and communication satellites, though 4 of those resulted in failures. The most influential and consequential effect Buran had on the world, though, has to be those RD-170 engines. US engineers heard rumours of the Soviets building oxidizer-rich closed-cycle engines, but no one really believed them. Remember, as far as the US was concerned, the Soviets lied about everything. US engineers visited Russia at the first opportunity to try and source these mythical engines. From every account I can find, they were stunned by the performance. Not only were US engineers forced to re-evaluate their design preconceptions, but also their working practices. The US government was keen to keep Russia's new surplus of rocket engineers busy and stop them defecting to somewhere like Iran or North Korea. And US companies were also extremely keen to get their hands on the Russian engines. The pinnacle of this collaboration was the RD-180. This is essentially 2 chambers from an RD-170 with a half-size turbopump assembly. It's powered the first stage of the American Atlas V rocket since 2000. If you grew up around the same time I did, almost every flagship space probe you can remember launched on either a Delta or an Atlas V. Before SpaceX revolutionized the medium launch market with the Falcon, the Atlas V, along with the Delta II, was the dominant lift vehicle in the US. Some examples of notable launches are on screen now. And a few days before I wrote this script, it launched 2 astronauts to orbit for the first time. It took nearly 40 years, but Energia's engines, or at least a direct descendant of them, finally put someone in orbit. To date, 100 Atlas V and 6 Atlas III launches have been carried out using RD-180 engines, with a 100% success rate. The Atlas family started life as the first US ICBM. They launched the first US astronauts to orbit, and then took a 60-year hiatus from crewed launches. They'll end life powered by Soviet-designed engines, with missions carrying crew to the International Space Station. I can't think of a better example of international cooperation. I'm not sure whether the flawless record of the RD-180 can be carried over to the RD-170, but it does suggest that with proper QA, Energia's launch boosters may not have been as liable to spontaneously explode as I like to make out. On to the AN-225. Its story almost ended with that of the Soviet Union. It sat for years semi-abandoned and gradually cannibalized for parts. But in the late 1990s, its owner Antonov Airlines saw a niche for an ultra-heavy lift aircraft and restored it back into service. Over the next 20 years, the aircraft carried a number of notable loads, including wind turbine blades, tram locomotives, and a power plant generator. It was used for aid relief on multiple occasions, most recently carrying supplies during the 2020 pandemic. Finally, remember the Bohr 4 test vehicle I briefly mentioned at the start of this video? The design was eventually adopted into Dream Chaser in the US. In my previous video, I actually erroneously stated Dream Chaser was derived from the shuttle. Okay, so it's not so bad after all. Years of cooperation and expanding human knowledge. A lasting, if somewhat melancholic legacy. So now it's time for me to ruin everything. Or for Vladimir Putin to ruin everything more correctly. For the past decade, Putin and his government have systematically destroyed and removed almost every remaining descendant of Buran. This of course began with the invasion of Crimea in 2014 and culminated with the full-scale invasion of Ukraine in 2022. Let's start with the obvious. The AN-225 was destroyed during the attack on Gostomel Airport. That was its base of operation. I never got to see it in person. and these images still really hurt me. The Zenit rocket was built in Ukraine, but the engines were Russian. Though a couple have been launched since 2014, these were existing stock. The Zenit will never fly again. The US began a switch from Russian engines in 2014, and Russia stopped selling them altogether in 2022, ending the collaboration that made the RD-180-powered Atlas V possible. A sorry end for some of the greatest engines ever built. In the long run, this may actually benefit the US, where multiple private companies have gone on to develop their own oxidizer-rich closed combustion cycle engines. SpaceX have even managed a full-flow stage combustion engine. In 2018, Russia appointed Dmitry Rogozhin, a neo-Nazi, as the director of Roscosmos. Though he was removed from the post in 2022, he's emblematic of a state gripped by totalitarian kleptocrats. I don't share my political views on this channel, but there's one exception I'm happy to share. If you live in a democracy, fight to keep it. OK-101, the Buran orbiter that went to space, was destroyed in 2003 when the hangar roof collapsed on top of it. A unique piece of spaceflight history gone forever. There is one more almost flight-worthy Buran in the world. It resides in an adjacent hangar along with a test article. If no action's taken, they'll also eventually be destroyed by another hangar collapse. It could happen today, it could happen in 20 years. Due to a frankly ridiculous dispute that I don't have time to go into now, ground crew at Baikonur are unable to remove the orbiters for preservation. All they need is to be lowered onto a trolley and towed out and placed under a temporary structure to keep them safe while the two kids sort out their differences. But they're unable to even agree to that. I told Artem that the hangar reminds me of the Chernobyl sarcophagus. And he said this, quote, "A sarcophagus contains something or someone dead. Important, never to be seen again. Knowing that those doors are blocked, Buran is truly in a sarcophagus." End quote. The final kicker. The person at the end of the dispute trying to rescue the orbiters from their sarcophagus is Rogozhin, a spark of goodness in a person truly broken by hatred. One of my earliest space memories is of my dad taking me out to the back garden to see Mir flying over. I didn't grow up in the Cold War, and the space race always just came across as political posturing to me. Even as quite a young child, I remember being in awe at the best of the achievements of the Soviet space program. I still am. A few years later, in 2009, I found myself in a conversation with a group of Russian soldiers. It was during the Nijmegen marches in the Netherlands. One of our group spoke Russian, and we were all in British military uniform. They were friendly, and I remember that event fondly. That's because for most of my life, up until 2014, Russia was not strictly an adversary. Sure, there were ideological differences, and sure, the Russian government were not a trustworthy friend, but the prevailing opinion was that the Cold War was over. The Soviet Union was gone, and the future was about us working together. Buran didn't get the good ending, but it didn't get the bad ending I started this video with either. But its remnants did force teams in the US and Russia to work together. I'd call it an okay ending. It was born out of fear, and the Soviets, in all honesty, couldn't afford it. Curious Droid eloquently puts it as a proportionate response to a phantom threat, but purely as a technological exercise, as a demonstration of engineering capability, somehow pulled off by a nation with a fraction of the manufacturing infrastructure of the US. I believe Buran was the most impressive thing the Soviet Union ever created. Now, almost every day I go for a run, and I very often run past that building there. And I may recognise it, because it was recently featured in the Tetris movie, portrayed as the headquarters of Elog, the Soviet organisation that owned the rights to Tetris. And what happens when you complete Tetris on level 9 with 5 lines?